We go ahead with the analysis of a popular shortwave antenna. Today it is about the operating mode as a 3-element Yagi antenna in the 20-meter band. We have got a few goodies that you've never seen before. Today it is about radiation diagrams and the influence of buildings in the vicinity. I think you haven't seen before an analysis of these depths. That motivated me to make this video. We investigate the properties of a popular shortwave antenna in the 20-meter band. I have already published a previous video on this antenna in which I examined its characteristics in the 40-meter band. I'm linking the earlier video on the top right corner. We will carry out the analysis with the program NEC. The questions are the same as last time, but I can tell you that we will see quite some more effects today. The antenna is tunable so that it can be used on all bands from 40 meter to 6 meter. In the 40 meter band mode, the antenna is reduced to a half-wave dipole, the properties of which we have discussed in detail in the last video. On the bands 20 meter to 6 meters, the antenna works as a 3-element yagi-uda antenna. And that's the mode that we are exploring today. When developing the wire grid model for the simulation, I noticed that the impedance of the antenna can be trimmed very well via the length of the director. You can use it to practically reach an ideal antenna matching. In fact, it actually works the same way in reality. I have to say, I like the principle of this antenna with the adjustable elements more and more. It's always good to know what the radiation pattern of an antenna would look like in free space. That's why I show the 3-dimensional radiation characteristics and the azimuth diagram here. Then we also have the elevation diagram, which is much wider. The gain is just over 6 dB, so the antenna has a good directivity, at least for this frequency range. So far we have only considered the antenna in free space. In reality, nearby obstacles and above all the ground play a major role so that the radiation characteristics look different from the one in free space. At least that's the case for low frequencies. I think I'll have to explain at some point why that's the case. What do you think? Should I? Write me in the comments. We want to find a suitable height for our antenna, and for this purpose I now calculate the radiation patterns for different heights. We model the ground as average ground in NEC. And off we go. At 5 meters above ground, the main lobe is strongly pushed up and has an elevation angle of about 45 degrees. This is quite unfavorable because we strive for a low radiation angle for long distance connections so that our radio waves can be better reflected by the ionosphere. With an antenna height of 10 meters above ground, we have a better situation. The elevation angle of the main lobe is well below 30 degrees. We also see that the antenna gain became a bit larger. So you almost get double benefit by putting the antenna a little higher. Wow, with an antenna height of 20 meters it gets even better. The elevation angle of the main lobe is only 15 degrees. At a height of 30 meters it would be only 10 degrees. And that would be great, of course, but a 30-meter antenna mast is quite a challenge in multiple sense, apart from the high cost involved. We are now going back to the 15 meters antenna height that we actually have. Then I'll show you the azimuth diagram, which by the way is almost not dependent on the antenna height. You already know our wire grid model for the private house from the last video. Although it is only a simple wire grid model, it is sufficient even in the 20 meter band to model the electromagnetic properties of a building well. The highlight of the wire grid model is of course the antenna that can be rotated. I explained how I realized this with NEC in the video at the top right. By the way, in case you were already wondering what the blue arrow down there means, it simply shows the north direction. It really helps to keep your orientation, especially when you've rotated and moved wire grid structures using vector transformation. Next, we analyze the antenna impedance. What happens if we rotate the antenna? Actually, nothing spectacular happens here. The matching can change slightly depending on the angle relative to the building. If you wanted, you could even compensate for that by adjusting the director. Now let's look at the azimuth diagram. The radiation pattern is obviously somewhat deformed. And besides that, the antenna gain varies between 10.3 dB and 11.7 dB, depending on the angle relative to the building. We can also see the frequency dependency in the graphic, since we have calculated the entire frequency range of the 20 meter band, which is from 14 MHz to 14.35 MHz. In the worst case, we could lose an additional 2 to 3 dB of the antenna gain as a result. We can also see these influences in the elevation diagram. Fortunately, however, the elevation angle of the main lobe doesn't change. Okay, now it's getting really exciting, because now we are taking the buildings in the neighborhood into account. In the vicinity of our amateur radio site, there are some buildings that are higher than our antenna height. What influence do these buildings have on the wave propagation? That's exactly what we are looking at now. First, we look at the azimuth plot in the far field. The diagram you see here was calculated at a distance of 5000 meters, which is much further away than the buildings. So the buildings are much too big on this scale, but they give us a good orientation. This helps us to explain the effects that we see in certain directions. In the azimuth diagram, we now see a ripple caused by reflections, and we also see shadowing effects from the large buildings. As a result, the signal level in the distance changes significantly depending on the radiation angle. There is also an additional frequency dependency, similar to the one that we saw a few minutes ago. However, the frequency dependency is hardly increased by the surrounding buildings. Cool, right? Of course, one suspects all these effects, but here we have finally quantified them. Now, of course, we also look at the elevation diagram. Like I said before, actually it is not the diagram of the antenna that we are talking about here, but the signal level of the sum of all reflections and diffractions at a great distance. Of course, we also see the signal fluctuation in the main beam direction, which depends on the horizontal beam angle. It is also interesting to see that at the moment when the radiation of the main beam becomes weaker, the side lobe becomes significantly stronger. And this can be explained as follows. If the radio waves are obstructed by a building, then there are also reflections and diffractions at that moment, which then propagate in a different direction. It's really nice what you can learn from this simulation. I like it very much. By the way, have you already liked the video? The insights. I summarize the results we got for the antenna in the 20-meter band. The height of the antenna above ground has a significant influence on the elevation diagram of the antenna in the 20-meter band. Your own building has a little influence on the impedance and the radiation patterns of the antenna. Reflections and diffractions by surrounding buildings have more influence in the 20-meter band than in the 40-meter band. The wave propagation is more obstructed as an effect of this. We have quantified a number of effects using an example. And I can tell you that they are not really significant in these frequency ranges. For instance, we don't see any total shadowing, which we would see in the gigahertz range. The obstruction of radio waves in this frequency range by buildings should not hold anyone from operating shortwave amateur radio. In case of uncertainties, this video might help a little to estimate this in your case. Occasionally, there will be further videos about antennas on this channel. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.